So we've just said that R squared is the set of, not numbers, but points, I think is a better way of describing it, in two-dimensional space. So all of the points on there. So R3 is the set of points in three-dimensional space. So you basically have the idea of an X and a Y and a Z axis, and we get to a point somehow by going along X, up Y, up Z. So, okay, all the points. Infinite, again, an infinite number of those. Question 2 in the book says, define a set B of all positive integers divisible by 2. So we say something like, all positive integers divisible by 2 . And we would do that. Again, the dot, dot, dot idea is to show that that pattern continues. Okay. Now we have the cardinality of a set. The cardinality of a set is the number of elements in the set. So, for example, the cardinality is often written like this: n of A is 5 if A is okay. The number of elements in set A is 5 if A is that. We've got 5 elements in the set, so this is the cardinality of the set. Here's the number of elements. Remember doing that GCSE maths? Mm-hmm. Right, so that's that. Now, some of the sets that we've talked about are actually have got infinite cardinality, haven't they? Okay, and we need to very briefly discuss. So let's say something like Z has infinite cardinality. And reals has infinite cardinality. However, they are different, and they have different sizes. Okay. The integers, the set of integers from minus infinity to infinity, is actually infinitely smaller than the set of real numbers. Alright, so we have this idea of something called countably infinite versus incountably infinite sets. If you can basically count them off one by one, then a set is countably infinite. Okay, so Z is countably infinite because they can be paired off with the integers. Now it seems pretty obvious that the set of integers is countably infinite because it can be paired off with the integers. We're going to do other integers. But we can't do that with the reals. Okay? We can't do that. reals, a set of reals is incountably infinite. Because if we try to start off with my reals equal something like this, 1, 2, and then I suddenly realise I need all the numbers between 1 and 2. So, maybe 1.5. But then I need all the numbers between 1.5 and 2, so I need 1.75. I need all the numbers between 1.7. Do you see what I mean? I go down a deep and dark hole. I never get to actually get to 2. Yeah, because I've got an incountably number of infinite numbers between 1 and 2. Because it doesn't matter how small a number I choose that's bigger than 1, there's always 1, which is between that number and the next one. So that's why it's an incountable number. I can't count them off. So I cannot count real set off with natural numbers or with integers. Let's do between countable infinite and incountable infinite. So how about the set of quotients? Is that countably infinite or incountably infinite? No, it's countably infinite because I've got basically a countable number for my numerator, a countable number for my denominator, and all I do is to say, okay, I've got all my infinite number of ones in my numerator and all my infinite ones in my denominator, both of which are countable. I can just put the sets end by end, and I can count those off with the integers. So this is countable. My natural numbers are countable infinite as well, obviously. Okay, set comprehension we need to do now. Let's do a separate thing for that. Set comprehension is a fancy way of saying a different set notation. So set comprehension it's basically how do we comprehend sets? How do we understand them? Is a notation for writing sets. So for example, we might write something like this. So let's try and read that in English. In English, this says the set A is the same as the set of x's, and this vertical bar here means such that, and then obviously x is greater than or equal to 5, and x is less than or equal to 8. Now you might also see that for and, sort of a caret, and that's also and it's sort of analogous to this intersection between, there's also and, isn't it? Yeah, if you remember from GCSE. Okay. You might also see a colon for the vertical bar. Mathematics, we use a colon. And that colon also means such that. Something like that.